Good evening, everyone. How is everyone doing? I'm glad that everyone is doing good. I'm doing well myself. So let's give it another minute or two for more of our friends to join us. But I'm glad to see the regular group is here and active as always. Mr. Visagie, what do you mean the segmentation's fault for CPP? Okay, I'm following. So yeah, pointers is one of the more difficult things to grasp in programming. The only course that's more horrible in programming is assembly. Because in assembly language, then you are working with the software registers itself, and it's a very, very, very low language. So it's horrible to work with. Data structures is actually very nice. So what is the best grade you got to complete in C++? Is that me or one of the students? Reasons I'm doing maintenance on the Wi-Fi and will be down from 7 o'clock, so unfortunately not be able to attend the end. Thank you for informing me that's 100%. No worries. So my C++ course I did in the first year, so I did my computer science degree at University of Johannesburg, so UJ. So for my C++ module in first year, I got a final mark of 94%. But C++ isn't that bad. It's just a way of thinking you need to get into, and then programming is a little bit easier. And Mr. Beekers, I will also take a look at that. So let's start with tonight's lecture. So it seems like not many students are going to join us this evening. Hopefully a few more will join in throughout the lecture. But last night we looked at planet formation. But now we're going to start looking at our own planets, the planets in our own solar system. And the best place to start is to form a travel guide to the terrestrial planets. So Mercury, Venus, Earth, Mars. But before we can look at those planets, we need to understand our own planet, so planet Earth, and also look at our own natural satellite, the Moon. So this is one of the first images of Earth that was sent back by the Apollo spacecraft. And what makes this image also extraordinary cool is this image was received first year in South Africa at the observatory where I am. So This is from the Hartebees Hoek Radio Astronomy Observatory that was built primarily in the 60s to do tracking and telemetry on the Apollo missions. So I saw a video today that said we have never seen a real picture of Earth. All the pictures have been edited to remove the satellites. No. We have seen, so there's a few actually cool images of those that we can see. So that depends on, the satellites are really small, so it depends on how their solar panels are positioned. Then you can sometimes see reflections of the solar panels, but that is so small compared to the reflected light from Earth that we rarely see satellites in photos unless you really search for them. So this image was received here in South Africa at Hartral. And what makes this image quite cool for back in the day, you'll see this image, it looks like it has been cut in these segments going from top to down. So, while taking the photograph, sending it back to Earth, this is actually sent back in different bits and segments. And each one of these strips resemble a certain sequence of bits, and that is sent back to us. This image is also known as Earthrise. Going back to another picture of the Apollo spacecraft, this is one of the more better pictures that we received from the Apollo missions. So in the preceding chapter, you learned how a solar system formed as byproduct of the formation of the sun. You also saw how distance from the sun determined the general composition of each planet. In this chapter, you begin the study of individual planets by comparing and contrasting Earth with its moon. On the way, you will answer 4 important questions. How do the Earth and its moon compare with other terrestrial worlds? How has Earth changed and evolved since it formed? Why is the moon airless, heavily cratered, and geologically inactive? And lastly, how are the histories of Earth and the moon connected? Planets are more alike than they are different. They are described by the same basic principles. You can compare and contrast them to identify those principles and understanding planets better. This approach is called comparative planetology. You can learn much more that way than by studying planets separately. So another branch of astronomy, I have a few colleagues doing it, is called planetary scientists, and they study planets and how they formed, how they evolve, and what happens on those planets. So Earth and its moon are ideal starting points for your study because they are respectively the largest and the smallest of the 5 terrestrial worlds. Earth is a complex planet with a molten interior that generates a magnetic field. Its crust is active with moving continents, earthquakes, volcanoes, and ongoing mountain building. Earth's oxygen-rich atmosphere and water-covered surface are unique in the solar system. In contrast, the moon is geologically inactive and has no atmosphere. Nevertheless, the histories of Earth and the moon are intertwined. You will meet the other 3 terrestrial worlds, Mercury, Venus, and Mars, in the next chapter, and find that many of their properties fit between the benchmarks set by Earth and the moon. If you visit the city of Granada in Spain, you will probably consult a travel guide. If it's a good guide, it will do more than tell you where to find museums and restrooms. It will give you a preview of what to expect. You're beginning a journey to the Earth-like worlds, so you should consult a travel guide and see what is in store. In this chapter and the next, you will visit Earth, Earth's moon, Mercury, Venus, and Mars. It may surprise you that a moon is included in your itinerary. It is, after all, just a natural satellite orbiting Earth and isn't one of the planets. But the Moon is a fascinating world of its own. It makes a striking comparison with the other worlds on your list. And its history gives you important information about the history of Earth and other planets. And through your assignment, you also learned a lot of information and interesting facts about the Moon as well. In Figure 16.1, compares the 5 worlds. The first feature you might notice is diameter. The Moon is small, and Mercury is not much bigger. Earth and Venus are large and quite similar in size, but Mars is a medium-sized world. You will discover that size is a critical factor in determining a world's personality. Small worlds tend to be geologically inactive, while larger worlds tend to be active. So here we can see these terrestrial worlds compared with one another. So the first thing we need to understand is the core, mantle, and crust. The terrestrial worlds are made up of rock and metal. Planetary scientists have evidence that they are all differentiated, which means each world is separated into layers of different density, with a dense metallic core surrounded by a less dense rocky mantle and a low density crust on the outside. As you learned in chapter 15, when the planets formed, their surfaces were subjected to heavy bombardment by leftover planetesimals and other debris in the young solar system. You will see lots of craters on these worlds, especially on Mercury and the Moon, many of them dating back to the heavy bombardment era. Notice that cratered surfaces are old. For example, if lava flow covered up some cratered landscape after the end of heavy bombardment, few craters could be formed later on that surface because most of the debris in the solar system was gone. When you see a smooth plane on a planet, you can be sure that surface is younger than a heavily cratered areas. Another important way you can study a planet is by following the energy flow. In the preceding chapter, you learned that a heat in the interior of a planet may be partially from radioactive decay and partly left over from a planet's formation. But in any case, it must flow outward towards the cooler surface where it is radiated into space. In this process of flowing outward, the heat can cause convection currents in the liquid interior, magnetic fields, plate motions, quakes, faults, volcanism, mountain building, and more. Heat flowing outward through the cooler crust makes a large world like Earth geologically active in contrast. The Moon and Mercury, both small worlds, cool quickly inside, so they have little heat flowing outward now and are relatively inactive. And what makes the terrestrial worlds also interesting and distinguishable is their atmospheres. When you look at Mercury and the Moon in Figure 16.10, you can see their craters, plains, and mountains clearly. Neither has substantial atmosphere to obscure your view. In comparison, the surface of Venus is completely hidden by a cloudy atmosphere and even thicker than Earth's. Mars, the medium-sized planet, has a relatively thin atmosphere. You might ponder two questions. First, why do some worlds have atmospheres while some do not? You will discover that both size and temperature are important. The second question is more complex. Where do those atmospheres come from? To answer that question in later chapters, you will have to understand the histories of these worlds. Now we're going to start to look at the 4 stages of planetary development. This is a good question to ask for the exam, so just a hint for you guys. Like the other terrestrial planets, Earth formed from the inner solar nebula about 4.6 billion years ago. Even as it took form, it began to change. There is evidence that Earth and the other terrestrial planets, plus Earth's moon, passed through 4 developmental stages. So the hint for the exam. So the first stage is differentiation. Differentiation produces a dense core, thick mantle, and low density crust. The young Earth was bombarded, so remember differentiation, bombarded, in the debris-filled early the solar system. Then flooding by molten rock and later by water can fill landforms. Then lastly, slow surface evolution continues due to geological processes including erosion. The first stage of planetary evolution is differentiation, the separation of material into layers according to density. In the next section, you will learn about evidence that Earth is differentiated, with a dense core plus a less dense mantle and crust. That differentiation is understood to have occurred due to melting of Earth's interior caused by heat from a combination of radioactive decay, plus energy released by infalling matter during the planet's formation. Once the interior of Earth melted, the densest materials were able to sink to the core. The second stage, cratering, could not begin until a solid surface formed. The heavy bombardment of the early solar system made craters on Earth just as it did on Moon and other planets. As the debris in a young solar system cleared away, the rate of cratering impacts decreased towards its present low rate. The third stage, flooding, began as radioactive decay continued to heat Earth's interior and caused rock to melt in the upper mantle, where the pressure was lower than in its deep interior. Some of that molten rock welled up through cracks in the crust and flooded the deeper impact basins. Later, as the environment cooled, water fell as rain and flooded the basins to form the first oceans. Note that on Earth, basins flooding was first by lava and later by water. The fourth stage, slow surface evolution, has continued for at least the past 3.5 billion years. Earth's surface is constantly changing as sections of the crust slide over and against each other, push up mountains and shift continents. In addition, moving air and water erode the surface and wear away geological features. Almost all traces of the first billion years of Earth's history have been destroyed by the active crust and erosion. Terrestrial planets pass through these four stages, but differences in mass, temperature, and composition among the planets can enhance some of those stages relative to the other stages and produce surprisingly different worlds. Earth is a good standard for comparative planetology. Every major process on any rock world in the solar system is represented in some form of Earth. Nevertheless, Earth is unusual among the planets in our solar system in several ways. More than 70% of Earth's surface is covered by liquid water. No other planet in our solar system has liquid water on its surface, although, as you will learn later chapters, Mars had surface water long ago, Venus probably did, and some moons in the outer solar system show evidence of having liquid water under their surfaces. So in your textbook, take a look at the celestial profile too. It has an extra lot of information on these four different stages. Your home planet is special in a second way. Some of the matter on the surface of this world is life, and a small part of that matter, that living matter, including you, is aware. As you will learn in chapter 20, life currently seems to be absent from other worlds in the solar system. No one is sure about all the ways that the presence of living matter has affected the evolution of Earth, but as you will later learn later in this chapter, that the thinking part of life on Earth, humankind, is actively altering our planet. Earth's interior You have read that there is evidence Earth is differentiated into a dense metallic core with lower density, rock mantle, and crust. What is the evidence? A very simple argument is based on the fact that Earth's average density, which can be calculated easily from its mass and volume, is 5.5 grams per cubic centimeter. But the silicate rocks on Earth's surface have only about half that density. Therefore, a large part of Earth's interior must be made of material much denser than crystal rock. Can more detailed information be determined about Earth's interior? What do you guys think? You guys are right, but how would we determine, how would we get that information? Yes, we can dig. Yes, seismology, X-rays. So yes, thinking about it, I don't remember in one of the first opening chapters, I made a joke and asked who of you have watched the movie The Core. Has anyone new watched the movie? Those that haven't, please do yourself a favor and watch The Core. It's on Netflix as well. It's an early 2000s movie, so 2000 sci-fi, but it is a brilliant movie. So let's take a look. Investigators, although even the deepest mines and wells extended only a few kilometers down and don't even reach the bottom of the crust, exploration of Earth's interior is possible because earthquakes produce vibrations called seismic waves that travel through the crust and interior and eventually register on sensitive detectors called seismographs all over the world. So before going on with this, do you guys know where some of the world's deepest mines are located? Yes, in South Africa, primarily here in Gauteng. Okay, the Mariana Trench is a naturally formed canyon, but so I speak of the deepest we've mined. So I haven't checked that in a while, but I think that was roughly 4.5 kilometers deep. Exactly. So think about the challenges of mining that deep. So the first and biggest problem will be heat. The deeper you go, the hotter it will be. Secondly, the pressure change. So the pressure will become higher. And then thirdly, you need to have constant flow of oxygen. So you need to have the mine cooled and oxygenated at the same time. So I don't know if you guys have ever watched the on Discovery Channel way back the show Extreme Engineering. Um, Extreme, so these South African mines, or the deepest mine in the world, it's here in South Africa, um, was on Extreme Engineering. Thanks, Mr. Van Berg, for the info. So, something interesting as well, speaking of seismographs. So there's, I've spoke about this in the opening chapters of this course as well, but there's a branch of astronomy called geodesy. So in astronomy, we use astronomy techniques to study the space, but geodesy uses astronomy techniques to study the Earth. So one of the techniques that geodesists use is tracking continental drift. So if you have a telescope and you point it to a quasar, and the following day the quasar's position all of a sudden has shifted, that means it's impossible for the quasar to shift its position in the night sky so dramatically that you have to readjust the telescope. So what it means is the telescope's position has changed. And that's how we track continental drift. And by doing those observations, we've determined the African continent is drifting towards India at a pace of around 2.2 centimeters per year. And geodesists also have a variety of seismographs installed across the country. So at the observatory, we can track seismic activity across the country. So we have a new technique called, that's developed here in South Africa by the Hartbeespoort Observatory. It's called a seismic vault. So the idea is that you build literally a vault 4 meters underground. And the vault is not big. The vault is about 2 by 2 by 2 meters. So you need its vault, so you want a vault as the foundation of the vault to be as stable as possible. And then in the vault, we put seismographs and seismic equipment. So seismograph basically tracks earthquakes and earth movement. So the prototype was built here at Hartbeespoort, and now currently we are installing them all over the country, and that will spread to across Africa as well. So that is actually quite cool. So usually when there's an earthquake that we feel like last year or two in the Gauteng region, we can actually pick it up from our seismographs and seismic vaults. And there's new law that came in 2019 that at every nuclear reactor there must be seismic equipment as well. So as we will now continue, in a seismograph gives information in two kinds and two sorts of wavefronts. So the kinds of seismic waves are important in this explanation. We have pressure waves, also shortened as P waves, travel as a series of compressions and uncompressions like sound, and can pass through liquid. In contrast, the shear waves or S waves travel as a type of side-to-side vibration that can't pass through a liquid. When an earthquake occurs, no direct S waves passes through the core to register on the seismographs on the opposite side of the Earth. But if the core was casting a shadow, the absence of S waves shows that the core is mostly liquid, and that the size of the S waves shadow shows that the outer boundary of the core lies slightly more than halfway between Earth's center and its surface. So here we will see P and S waves gives you clues to the structure of Earth's interior. No direct S waves from an earthquake reaches the side of the Earth, so one side to the other side. Opposite side source indicating that Earth's core is liquid. The size of the S wave shadow tells you the size of the liquid outer part of the core. The P and S waves caused by an earthquake do not travel in straight lines or at constant speed within Earth. The waves may be reflected off boundaries between layers of different density, or they may be refracted as they pass through a boundary and their speed is greater in regions of high temperature and density. Geoscientists can use the arrival times of reflected and refracted seismic waves from distant earthquakes to construct a detailed model of Earth's interior. Such studies confirm that the interior consists of three parts: a central core, a thick mantle, and a thin crust. Mathematical models based on the seismic data indicate that the core is hot, about 6,000 Kelvin, dense, about 13 grams per cubic centimeter, and composed of iron and nickel. The core of Earth is as hot as the gases at the sun's surface. But high pressure keeps the mantle solid near the center of the core and liquid in its outer part. Earth's magnetism gives you further evidence about the core. The presence of magnetic field is clue that part of Earth's core must be liquid metal. Convection currents stir the liquid, and it also rotates as Earth rotates. Because of these motions, and because it is a very good conductor of electricity, the liquid, our core, generates a magnetic field through the dynamo effect, a different version of the process that creates the sun magnetic field, and we've learned in the previous chapter. From traces of magnetic fields retained by rocks that formed long ago, geologists conclude that Earth's magnetic field has reversed itself in an irregular pattern, on average a few times per million years. Occasional reversals, though poorly understood, seem to be a characteristic of the dynamo effect. The paths of seismic waves in the mantle, the layer of dense rock that lies between the molten core and the crust, show that it is not molten, but it is not really solid either. Mantle material behaves like plastic, a material with the properties of a solid but capable of flowing under pressure. The asphalt used in paving roads is a common example of a plastic. It shatters if struck with a sledgehammer, but it bends under the steady weight of a heavy truck. Just below Earth's crust, where the pressure is less than at greater depths, the mantle is most plastic. Earth's crust is composed of low-density rock that floats on the mantle. The image of a rock floating may seem odd, but recall that a rock of the mantle is very dense. Also, just below the crust, the mantle rock tends to be highly plastic. So great sections of low-density crust do indeed float on the semi-liquid mantle, like great lily pads floating on a pond. The crust is thickest under the continents, up to 60 kilometers thick, and thinnest under the oceans, where it's only about 10 kilometers thick. Unlike the mantle, the crust is brittle and can break when under stress. The motion of the crust and the erosive action of water make Earth's crust highly active. And notice 3 important points in 6 new terms we do now, but before we continue on, have you guys actually stumbled across that Earth's magnetic field has swapped around in the past? So in your spare time, go read up about it. That's actually a very interesting effect of the dynamo effect inside our Earth's core that generates our magnetic field. So every couple of million years, the North and South Pole actually swaps around. So first on the list of new things we're going to learn is plate tectonics. The motion of crustal plates produced much of the geological activity on Earth. Plates spreading apart can form rift valleys, or on the ocean floor, mid-ocean rises where molten rock solidifies to form basalt. A plate sliding into a subduction zone can trigger volcanism, and a collision of plates can produce folded mountain ridges. Chains of volcanoes, such as the Hawaiian Islands, can result when a plate moves horizontally across a hotspot. Secondly, notice how the continents on Earth's surface have moved and changed over periods of hundreds of millions of years. 100 million years is only 0.1 billion years, 1/46 of the age of Earth. So sections of Earth's crust are in rapid motion from the perspective of a geologic timescales. Thirdly, most of the geological features you know, mountain ranges, the Grand Canyon, and even the familiar outline of the continents, are recent products of Earth's active surface. Earth's surface is constantly renewed. The oldest rocks on Earth, small crystals of the minimal zircon from Western Australia, are 4.4 billion years old. Most of the crust is much younger than that. Most of the mountains and valleys you see around you are no more than a few tens of million years old. You can see that Earth's dramatic geology is dominated by two processes. Heat rising from interior drives plate tectonics. Just below the thin crust of solid rock lies a semi-molten layer with motions that can rip the crust to fragments, push the pieces about like rafts of wood on a pond, and sometimes crash them together to raise mountain ranges and grow continents. The second process modifying the crust is water. It falls as rain and snow and tears down mountains, erodes river valleys, and washes soil and rock into the sea. Tectonics build up mountains and continents, and then erosion rips them down. You can tell the story of Earth without mentioning its atmosphere. Not only is it necessary for life, but it's also intimately related to the crust. It affects the surface through erosion by wind and water, and in turn, the chemistry of Earth's surface affects the composition of the atmosphere. A modern understanding of planet building is that Earth formed so rapidly that it was substantially heated by the impacts of infalling material, as well as by radioactive decay, so the young Earth would have been highly volcanically active. When a volcano erupts, 50 to 80% of the gas released is water vapor. The rest is mostly carbon dioxide, nitrogen, and small amounts of sulfur gases such as hydrogen sulfide. The rotten egg gas you smell if you visit geothermal pools and geysers such as those at Yellowstone National Park. If Earth's surface was molten as it formed, then outgassing would have been continuous, and Earth's original primary atmosphere would have been rich in water vapor, carbon dioxide, and nitrogen. Astronomers also have suspected that some of the abundant water on Earth arrived late in the planet's formation process as a bombardment of violet-rich comets. Spectroscopic studies of comets revealed that some comets, such as Comet Hartley 2, which was visited in 2010 by the Deep Impact Probe, have ratios of deuterium to hydrogen matching the ratios in the water on Earth, while other comets do not. Details of the origin of Earth's atmosphere and oceans are yet to be fully understood and are subjects of current research. The atmosphere you breathe is now a secondary atmosphere, produced later in Earth's history by chemical reactions between the atmosphere, crustal rocks, and surface water, and by green plants producing oxygen. Carbon dioxide is easily soluble in water, which is why carbonated beverages are so easy to manufacture. So the early oceans began to absorb atmospheric carbon dioxide. Once in one in the solution, the carbon dioxide reacts with dissolved substances in the seawater to form silicon dioxide, limestone, and other mineral sediments in the ocean floor, freeing the seawater to absorb more carbon dioxide. Thanks to those chemical reactions in the oceans, most of the carbon dioxide was transferred from Earth's atmosphere to seafloor sediments. When Earth was young, its atmosphere had no free oxygen, that is, oxygen not combined with other elements. Oxygen is very reactive and quickly forms oxides in the soil or combines with iron and other substances dissolved in water. Only the action of plant life keeps steady supply of oxygen in Earth's atmosphere via photosynthesis, which makes energy for plants by absorbing carbon dioxide and releasing oxygen. Beginning about 2 to 2.5 billion years ago, photosynthetic plants in the oceans had multiplied to a point where they made oxygen at a rate faster than chemical reactions could remove it from the atmosphere. After that time, atmospheric oxygen increased rapidly. So this topic will be discussed in our last chapter. It is a common misconception that there is life on Earth because of oxygen. The truth is exactly the opposite. There is oxygen in Earth's atmosphere because of life. Most life forms on Earth do not need oxygen, except a minority of creatures that are animals, including us. And some are even poisoned by it. Once the atmosphere began to contain abundant ordinary oxygen, Earth's lower atmosphere became protected from solar ultraviolet radiation by an ozone layer about 15 to 30 kilometers above the surface. Ozone molecules are very good at absorbing ultraviolet photons. An ozone molecule consists of 3 oxygen atoms linked together. Before there was oxygen, an ozone layer could not form, and the sun's ultraviolet radiation was able to penetrate deep into the atmosphere and break up weaker molecules such as water. The hydrogen from the water then escaped to space, and oxygen formed oxides in the crust. Earth's atmosphere could not reach its present stable composition until it was protected by an ozone layer, and that required oxygen. So what is the human effects on the atmosphere and climate? You can live on Earth's surface because of Earth's atmosphere, but modern civilization is altering Earth's atmosphere in at least 2 serious ways: by adding carbon dioxide and by destroying the ozone layer. The concentration of CO2 in Earth's atmosphere is important because CO2 can trap heat in a process called greenhouse effect. When sunlight shines through the glass roof of a greenhouse, it heats the benches and plants inside. The warmed interior radiates infrared radiation, but the glass is opaque to infrared. Warm air in a greenhouse cannot mix with cooler outside, so heat is trapped within a greenhouse and the temperature climbs until the glass itself grows warm enough to radiate heat away as fast as the sunlight enters. This is the same process that heats a car when it's parked in the sun with the windows rolled up. So here we can see the greenhouse effect. But here we can see the number of CO2 particles, or parts per million, in our atmosphere. And here we started reaching the Industrial Revolution, and we can see a dramatically increase in carbon dioxide in our atmosphere. Earth's atmosphere is transparent to sunlight. And when the ground absorbs the sunlight, it grows warmer and radiates at infrared wavelengths. However, CO2 makes the atmosphere less transparent to infrared radiation. So infrared radiation from the warm surface is absorbed by the atmosphere and cannot escape back into space. That traps heat and makes Earth warmer. CO2 is not the only greenhouse gas. Water vapor, methane, and other gases also help warm Earth, but CO2 is most important. It is a common misconception that a greenhouse effect is only bad. Evidence indicates that Earth has had a greenhouse effect for its entire history. Without a greenhouse effect, Earth presently would be at least 30 degrees Celsius colder and uninhabitable for most living things, including humans. And that brings me to interesting points. So I don't know how you guys follow general statistics. So I follow statistics of a few things, and here in South Africa, this current winter we are in is at average 6 degrees Celsius warmer than previous winters. So yes, so that 6 degrees is only in Gauteng. So Gauteng is 6 degrees warmer than usual. But in other places, yes, it can be cooler, and that is due to global warming, unfortunately. And then there are still people out there that is deniers of global warming. So everything is to do with global warming, but that's just something interesting. For 4 billion years, natural processes on Earth have removed CO2 from the atmosphere and buried the carbon in the forms of limestone, coal, oil, and natural gas. Since the beginning of the Industrial Revolution in the late 18th century, humans have been digging up lots of carbon-rich fuels, burning them to get energy and releasing CO2 back into the atmosphere more rapidly than it can be naturally removed, thereby increasing the intensity of the greenhouse effect. The increased concentration of CO2 is increasing the greenhouse effect, and warming Earth is what's known as global warming. So is it true that cow farts are destroying the ozone layer? So it's not destroying the ozone layer, but methane is a greenhouse gas. So yes, cows produce huge amounts of methane, especially on big farms and ranches. So yes, but what is actually destroying the ozone layer is past the CFCs in aerosol cans. So usually, that was when I was in primary school. You still had deodorant cans that make use of CFCs, and refrigerators, freezers also made use of CFCs. And what happens is CFCs, if they are released in the atmosphere, they rise up to the ozone layer, and then the CFC molecule actually binds with the ozone layer. So it forms a new molecule, and then the ozone becomes actually less, and that is what destroys the ozone layer. Yes, Mr. Bonolo.
Say, may I ask how does the ozone layer trap ultraviolet, like its structure?
How does the ozone layer do what?
Trap ultraviolet.
Oh, trap ultraviolet. Okay.
Yes.
So let's go back a couple of slides. So what happens is we have the ozone layer. So remember, the easiest way to probably describe this is by going back to our general form of antenna design. So if we have a wavelength or frequency, doesn't matter what it is, we represent it usually by making use of a sine wave. So when we speak of ultraviolet radiation, we usually imagine it as one of these sine waves. So what happens is if we have a layer, so let's call the ozone layer, and that's around Earth, and we have our incoming ultraviolet radiation. So now it all depends on what is the density of the ozone layer, and what happens with the molecules. So there's a few things that can happen with ultraviolet radiation. It all depends on the incident angle. It can be reflected off the ozone layer, or it can pass through the ozone layer. So what's happening is there are two processes happening. The one is it hits the ozone layer and is reflected back in space, but at incident angles, it hits the ozone layer and then it reacts with the ozone layer, and the ultraviolet radiation is then dispersed along the molecules in the ozone layer, and nothing happens with it. Does that answer?
Yes, that it does.
Awesome.
Thank you.
Pleasure. So let's go back to the slides. Where were we? Okay, so this is where we were. So I saw So haven't CFCs been banned the 1980s? Yes, so CFC were international treaty that started banning CFCs in the 1980s, but not all countries have signed it during that time. I think South Africa signed it only in the late 1990s and early 2000s. Studies of growth rings in very old trees shows that the average Earth climate has been cooling for most of the last 1,000 years. By the 20th century, reversed that trend with a rise of 0.56 and 0.92 degrees Celsius. Mountain glaciers have melted back dramatically since the 19th century. Measurements showed that polar ice in the form of permafrost, ice shelves, and ice on the open Arctic Ocean is melting. No, so currently no countries are making use of CFCs. Yet another common misconception is that the observed warming of the Earth is due to natural causes rather than a greenhouse effect. As scientists began to study early indications that Earth's global climate is warming and that human-produced CO2 might be a major cause, they created with professional skepticism, reactive professional skepticism. They also, in your textbook, you say, how do we know is a good read explaining this as well. So they ask questions such as, is global warming really happening? And if the warming is real, is some mechanism other than human activity the main cause? Experiments were conducted, calculations performed, and models created to answer those types of questions. Such research, carried out over decades, revealed that regular and predictable changes in Earth's axis, inclination, and orientation, and in the shape of its orbit, called the Milankovitch cycle. So currently we would be driving Earth's climate toward lower, not higher temperatures. Also, observations by space probes indicate that the sun's luminosity, average over its activity cycles, has been constant for decades or has decreased slightly. The observed warming must be strong to be occurring in the face of opposing astronomical effects. The amount of warming to expect in the future is difficult to predict because Earth's climate is critically sensitive to a number of different factors, not just the abundance of greenhouse gases. For example, a slight warming should increase water vapor in the atmosphere, and although water vapor is another greenhouse gas that would enhance the warming, increased water vapor might cause added cloud cover, increasing Earth's albedo, the fraction of light it receives that is reflected back to space. An increased albedo would tend to reduce the warming. Also, even small changes in temperature can alter circulation patterns in the atmosphere and in the oceans, and the consequences of such changes are very difficult to model. The situation is complex, but models that best track the warming that has already happened point to substantial continued warming. There is no doubt that civilization is warming Earth through an enhanced greenhouse effect, but the remedy is difficult to imagine. Reducing the amount of CO2 and other greenhouse gases released to the atmosphere is difficult because modern society depends on burning fossil fuels for energy. Political, business, and economic leaders may argue that the issue is uncertain, but all around the world scientists of stature have reached agreement. Global warming is real. It is driven by human activity and will change Earth. What humanity can or will do about it is uncertain. That brings me to a different point. So we already have the technology here on Earth to go green. So we have wind power, solar power, and nuclear power, and that is the way for the future. But unfortunately, that change is very slow due to political and industry, because they are making too much money out of fossil fuels and won't stop the process. So unfortunately, that is the wrong mindset. So that is why some companies such as what about cost as well? So contrary to belief, running costs for green energy in the long run is much cheaper than fossil fuels. So if you look at the average life cycle of a coal power plant is about 25 to 30 years, then the coal power plant is redundant and needs to be upgraded entirely. Where you look at nuclear and wind turbines, solar arrays, you have a much longer lifetime on those equipment, and that becomes cheaper the longer you run it. And that's also why there's a big shift now to electric vehicles. So compared to electric cars, do you think that combustion engines really contribute more to emissions than coal burning? So combustion engines is a big contribution factor to global warming. I am a big supporter of electric cars. If there's a big or proper electric car available in South Africa, such as Tesla, I will be one of the first people to sign up to get a Tesla. Also across our country, for example, now from Pretoria to Cape Town, every 200 kilometers there are now charging points. So a big contract or tender was awarded to a company to install charging stations. So I'm a big fan of those. And if you look at company brands such as the Volkswagen Group, so Volkswagen owns Lamborghini, they own Audi, they own Porsche. So Volkswagen said this 2022 will be the last year they developed internal combustion engines. So the engines they have are the ones they will continue using. And then by 2030, they want all their vehicles to be replaced by electric vehicles. And speaking about nuclear, so I have spoken about this in a previous lecture as well. People don't really know how nuclear power works, and that's why they are afraid of it. So nuclear power is one of the most cleanest ways to generate huge amounts of energy. So remember when we have a nuclear before we start a nuclear reactor, we need to keep in mind the law of matter. So matter cannot be created or destroyed. It can just be transformed from one form to another. So what people don't realize is a nuclear power plant, if you put in 1 kilogram of enriched uranium-235, you get 1 kilogram of waste out. And what people also don't realize is a typical nuclear power plant uses 2 kilograms of uranium in 5 years. So the amount of waste is extremely small that you get out, and the way to store it. So the way we dig deeper in the Earth's core, the ground becomes radioactive due to the core. So the deepest mine, so if you dig deeper, so if you start reaching about 3 kilometers deep in Earth's mantle, then the ground literally becomes radioactive. So what do? You dig deep enough and you store the radioactive waste there. So you have radioactive waste in radioactive ground already that is naturally occurring. So there's no harm done. So I'm a big fan of nuclear power, and the sooner people started realizing it, and the sooner people stop forming misconceptions on nuclear power, the better. So when electric cars become more mainstream, then you think the emissions will be the same? No. because electric cars don't have any emissions. So what about power plants? So power plants, so when you look at a nuclear power plant, you have zero emissions from a nuclear power plant. The only thing that you have from nuclear power plants is water vapor from the cool down towers. Yes, Mr. Visagi.
So I'm just thinking though, if we were to have electric cars in South Africa, I'm just behind the politics of it all. Would it really be more greener though, if, especially with all the Eskom issues, etc.?
Yes, it will be more greener. So I haven't checked, but I know there's a, last time I've checked, there is something like 80 million or 100 million vehicles in South Africa. So if you remove those vehicles, you instantly stop CO2 emissions from those vehicles. So Eskom is being sorted out. So that is the one problem, and that's a problem usually most people ask about. But that's the best way to go. And what people don't realize is, yes, Mr. Visagi.
So, but I was just thinking, wouldn't it cause less generation of power and less use of resources if we could have better sustainable public transport rather than private transport?
That will also help, but then again, we will need public transport that makes use of green energy. So the ones that's looking here at the comments, so yes, people are scared of nuclear power. So yes, it's true. There has been a few places where a nuclear power plant went bad. I think the most prominent one is probably Chernobyl. And in the US, it's what's it, Long Island. But overall, it's still one of the greenest uses of power. And then the reason why while we haven't got Teslas in South Africa yet, is due to political reasons. So the government currently is 3 Mile Island. Thank you, Mr. Groenewald. So currently, the government taxes Tesla 47% per vehicle if they are imported to South Africa, and that's why there's no dealership yet, because Elon Musk said he's not going to pay that much on tax. Yes, that's why we don't have Teslas in South Africa, because the government is taxing Tesla 47% per vehicle. Yes, Mr. Visagi.
So I was reading about a story where I think it was Israel or some other company, I think it's a European company, where we've got these offshore ships that are now giving us electricity. What is your take on
So,
that?
so yes, they're still deciding on that contract being awarded. But the idea is that there are power stations built on ships making use of natural gas and coal, and you just anchor them at a harbor, you connect it to the grid, and then you have basically a new power station that can produce power. So that is a good option for the short term, but it doesn't solve the problem of renewable energy. So yes, Mr. Gutierrez, that's politics makes everything better. And Mr. Mbaki, true, only bad things get published from nuclear in the news, but that's why we need science engagement to change people's minds on nuclear energy. So what do you think about the Dyson sphere? That is something we're going to discuss in the last lecture of this module. And yes, I failed to see the bigger picture. So do you guys want to take a quick 5-minute break? Okay, let's take a break and we can continue class at 6:40. So while we are taking a break, something a bit off topic, um, you guys listen to Star Talk of Neil deGrasse Tyson? So that is something I recommend you guys to listen to in your spare time. It's completely free to listen to. If you can use any music app that has access to podcasts, you can use Google Podcasts, Apple Podcasts, it's even on YouTube. Star Talk, there's an episode every week. So I listened to the latest episode, the second latest episode today while I was driving. And it was an amazing chat with Professor Richard Dawkins. Would it be breaking any rules if I were to publish my astronomy notes on a website? No, you're more than welcome to. Another thing to sort out is also airplanes, air pollution. So contrary to belief, if you look at comparisons, airplanes doesn't produce that much air pollution. Oh, Chuck Nice and Star Talk. No, depending on person, but sometimes Chuck Nice can be really. But another cool podcast you guys can also listen to is Science Rules of Bill Nye the Science Guy. So when do I find time to listen to podcasts? So I listen to podcasts when I'm traveling around. So from where I live, it is about 40 k's to the observatory. And from where I live, it's about 60 k's to UP. So either way, I'm traveling every day, either to the observatory or either to UP or either to both. So then I'm about an hour, hour and a half in a car every day. So then I listen to podcasts. Yeah, Cosmos was a great show. That is a very good question. So, do you think the human race will end themselves before natural phenomena takes us out? Um, I don't think so because we can reason with each other and caution everything. Um, if you have time, go read about the doomsday clock. That's also something interesting. The Joe Rogan podcast is also very entertaining. I haven't listened to it in a while, but that's also a great podcast. So the most podcasts are on science rules and Star Talk. Jordan, that's also a good podcast. Oh, wow. That is a lot of money he saved. Oswald's calculus chat. So it's 20 to 7, so we can continue with our lecture. So human influence on Earth's atmosphere go beyond the greenhouse effect. Our modern industrial civilization is also reducing CO ozone in Earth's atmosphere. Many people have a common misconception that ozone is bad because they hear it mentioned as a pollutant of city air. Produced by odor emissions, breathing ozone is bad for you, but as you learned earlier in this chapter, the ozone layer in the upper atmosphere protects the lower atmosphere and Earth's surface from harmful UV photons. Ozone is an unstable molecule. Certain chemicals called uh, chlorofluorocarbons, CFCs, used for refrigeration, air conditioning, and some industrial processes, can easily destroy ozone. As these CFCs escape into the atmosphere, they become mixed into the ozone layer and convert the ozone back to normal oxygen molecules. Ordinary oxygen does not block ultraviolet radiation, so depleting the ozone layer causes an increase in ultraviolet radiation at Earth's surface. In small doses, ultraviolet radiation can produce suntan, but in large doses, it can cause skin cancers. The ozone layer is especially sensitive to CFCs over the Antarctic and Arctic regions because of their temperatures. Starting in the late 1970s, the ozone concentration fell significantly over the Antarctic, and a hole in the ozone layer developed over the continent each October at the time of the Antarctic Spring. Satellite, airborne, and ground-based measurements showed the same thing beginning to happen at far northern latitudes. With the amount of ultraviolet radiation reaching the ground increasing. Fortunately, as a result of these warnings, international agreements banned most uses of CFCs, and the trend of ozone hole expansion slowed and now appears to have reversed. So here we can see average data from 4 years in the 1970s show no ozone hole, and then average data from 4 years in the 1990s showed a rapid development of an ozone hole. Yet there is another common misconception that global warming and ozone depletion are two names for the same thing. Take careful note that ozone hole is a second Earth environmental issue that is basically separate from global warming. The CO2 and ozone problems in Earth's atmosphere are paralleled on Venus and Mars. When you study Venus in chapter 17, you will discover a runaway greenhouse effect that has made the surface of the planet hot enough to melt lead. Also in chapter 17, you will learn that Mars has an atmosphere without an ozone layer. A few minutes of sunbathing on Mars would kill you. Once again, you can learn more about your own planet by studying exaggerated conditions on other planets. So on your own time, you can go through this celestial profile of both the Earth and the Moon. If you had been one of the first two people from Earth to step onto the airless surface of the Moon, what would you have said? Neil Armstrong responded to that destroyed significance of the moment by saying that's one small step for man, one giant leap for mankind. Buzz Aldrin was second, and he responded to the moon itself saying, beautiful, beautiful, magnificent desolation. In other words, although it is desolate, the moon has its own kind of beauty. Many planets in the universe probably look like Earth's moon, and astronauts may someday walk on such worlds and compare them with Earth's moon. Only 12 people have stood on the moon. That planetary astronomers know it well. The photographs, measurements, and samples brought back to Earth paint the picture of an ancient battered crust and a world created by a planetary catastrophe. The surface of the moon is divided into two dramatically different kinds of terrain. The dark grey areas visible from Earth by the naked eye are smooth lunar lowlands, which, using the Latin word for seas, early astronomers named Maria, plural for mare, which is produced Mare. You can also see the comparatively bright, rugged, and heavily cratered lunar islands. The color of the moon rocks is dark grey, but Earth's moon look quite bright in a night sky. In fact, the average albedo of Earth's moon, the fraction of the light that it reflects, is only 0.12. In other words, the moon reflects only 12% of the light of the sunlight that hits it. In comparison, Earth, thanks mostly to its bright clouds, has an average albedo of 0.31. The moon looks bright only in contrast to the night sky. In reality, it is dark grey world. Wherever you look on the moon, you find craters. These craters look quite dramatic near the terminator, the name for the boundary between daylight and darkness on the moon, where shadows are long. As you have already learned, the highlands are heavily marked by craters, whereas the smooth lowlands contain relatively few craters. Planetary scientists now know that the craters on the moon were formed by the impact of meteorites. The study noticed 3 important points plus 5 new terms. Impact craters have certain distinguished characteristics, such as their shape and the ejecta rays and secondary craters around them. Lunar impact craters range from tiny pits formed by micrometeorites to giant multi-triggered basins. Most of the craters on the moon are old. They were formed long ago when the solar system was young. 12 Apollo astronauts visited the lunar lowlands and islands between 1969 and 1972. Most of the rocks they found were typical of hardened lava, and some were vesicular basalt, which contains holes formed by bubbles in molten rock. These bubbles are made when lava flows out into the surface, and the lower pressure allows gases dissolved in the molten rock to expand and form bubbles. The same thing happens when you open a bottle of carbonated beverage and bubbles form. The presence of vesicular basalt showed that much of the surface of Earth's moon has been covered by successive lava flows. And the dark flat plains of lunar lowlands, the Maria, are actually solidified ancient lava. The islands, in contrast, are composed of rock containing minerals that have low density and would be among the first to solidify and float to the top of molten rock. For example, the islands are rich in anorthosite and light-colored and low-density rock that contributes to the highlands' bright contrast with the dark lowlands. So here we can see images of the Apollo 11 landing, Apollo 17, and certain places that were named on the moon. No, the moon cannot be hollow, because we can measure the density of the moon. We know what the weight of the moon is, so therefore we know what is its composition. So here in the lunar geology, we can see the Apollo astronauts and some of these rocks with bubbles in them. Many of the rocks all over the moon are breccias, rock made of fragments of broken rock sediment together under pressure. The breccias show how extensively the lunar surface have been pounded by meteorites. Nowhere did the astronauts find what could be called bedrock. The entire surface of Earth's moon is fractured by meteorite impacts. Moreover, as the astronauts bobbed across the lunar surface under its low gravity, their boots kicked up the powdery dust. This lunar dust is produced by a continuous bombardment of the lunar surface by tiny meteorites that slowly grind exposed rocks into fine grey grit with a consistency like talcum powder. The ALCROSS Lunar Crater Observation and Sensing Satellite mission discovered that at least one permanently shadowed region near the moon's south pole, there is a significant amount of water ice under the surface dust layer. Mr. Bekers, what do you mean echo? Over the last 2 centuries, astronomers developed 3 different hypotheses for the origin of Earth's moon. The fission hypothesis proposed that a moon broke from a rapidly spinning young Earth. The condensation hypothesis suggested that Earth and its moon condensed from the same cloud of matter in the solar nebula. The capture hypothesis suggests that a moon formed elsewhere in the solar nebula and was later captured by Earth. Each of these ideas had problems and failed to survive comparison with all the evidence. In the 1970s, based substantially on analysis of newly available lunar rock samples, a new hypothesis originated that combined some aspects of the 3 older hypotheses. The large impact hypothesis proposed that a moon formed when a very large planetesimal, estimated to have been at least as massive as Mars, smashed into the proto-Earth. Such a collision would have ejected debris into space, and model calculations indicate that some of the debris would have settled into a disk in orbit around Earth. The material in the disk would then have quickly collected to form the moon. So there was an experiment where an explosion on the moon caused echoes that lasted for 3 hours, and if I understand correctly, it is still not completely explained, so I'm not sure about it. So I will read up about it and get back to you in our next lecture. This hypothesis explains several phenomena. If the collision occurred off-center, it would have spun the Earth-Moon system rapidly, and would thus explain the present high angular momentum. If the proto-Earth and impactor had each already differentiated, the ejected material that became the Moon would have been mostly iron-poor mantle and crust, which would explain the Moon's low density and iron-poor composition. Furthermore, the material would have lost its volatile components while it was in space. So the Moon also would have formed lacking volatiles, as was noted in the Apollo rock samples. Such an impact would have melted the proto-Earth, and the material falling together to form the Moon would also have been heated hard enough to melt. This fits the evidence that a highland and ophrosite in the Moon's oldest rock formed by differentiation of large quantities of molten material. The large impact hypothesis survives comparison with the known evidence and is now considered likely to be correct. The 4-stage history of Earth's moon is dominated by a single fact that makes its unfolding noticeably different from Earth's history. In the later stages, the moon is small, only 1/4 the diameter of Earth. Its escape velocity is low, so the moon has been unable to hold any atmosphere. It cannot have surface water, and its interior cooled rapidly as its internal heat flowed outward into space. Small worlds have less heat and lose it more rapidly, so the moon's small size has been critical in determining its history. The Apollo moon rocks, especially an ophrosite from the highlands, show that a moon must have formed in a molten state. Planetary geologists now refer to the exterior of the newborn moon as a magma ocean. Magma is a term for molten rock in general, whereas lava means molten rock flowing on the surface of a world. Denser materials sank to the bottom of the magma, and as the magma cooled, low-density minerals floated to the top to form a low-density crust. In this way, the moon partially differentiated. The radioactive ages of moon rock, brought back by the Apollo astronauts, showed that the surface solidified about 4.4 billion years ago. The second stage cratering began as soon as the crust solidified, and the older highlands show that cratering was intense during the heavy bombardment period at the end of planet building. The moon's crust was shattered, and the largest impacts formed giant multi-rigged crater basins, hundreds of kilometers in diameter. The basins that became Mare Imbrium, so meaning sea of rains, for instance, was blasted out by the impact of an object about the size of Rhode Island. The Imbrium event occurred about 4 billion years ago and blanked 16% of the moon with ejecta. So this is near the heavy bombardment, a gigantic created vast crater basin. Faulting in the crust producing rings of mountains and lava flows fill the lowest regions. And then lastly, today all the outlines of the impact have been covered by dark lava flows. By counting craters on different parts of the moon and calibrating those data using radioactive ages of lunar rock samples, planetary scientists have been able to chart the decline of cratering over the first billion years of the solar system's history. By about 3.8 billion years ago, the impact rate had decreased to the current low rate. But before that, there seems to have been sudden burst of cratering astronomers call the Late Heavy Bombardment that might have included the Imbrium event. The primary evidence of this late bombardment comes from observations of the moon, but that sudden storm of impacts must have affected all of the planets in the solar system, including Earth. Those craters on Earth were erased long ago, but they can be seen on other worlds such as Mercury, Mars, and some of the moons in the outer solar system. To understand what astronomers think caused the late heavy bombardment, you'll need to learn more about the formation and evolution of Uranus and Neptune in Chapter 18. Astronomers can calculate that the tremendous impacts that formed the lunar basins would have cracked the crust to depths of 10 kilometers or more and led to the third stage, flooding. Through Earth's moon cooled rapidly after its formation, radioactive decay continues to heat lunar subsurface material as it did inside Earth. Parts of the lunar mantle and lower crust remelted, producing lava that followed the cracks up into the giant basins. The basins were flooded by successive lava flows of dark basalt from 3.8 to 3.2 billion years ago, thus forming the Moria. So here we can see much of the near side of the moon is marked by large, generally circulated lava plains called Moria. The crust on the far side is thicker and there is much less flooding. Even the huge South Pole Aiken basin contains little lava flooding. In these maps, color marks evolution, with red the highest regions and purple the lowest. Studies of the moon show that its crust is thinner on the side toward Earth, perhaps due to tidal effects. Consequently, while lava flooded the basins on the earthward side, it was unable to rise through the thicker crust to flood the lowlands on the far side. One of the largest known impact basins in the solar system is the moon's south pole, Aitken Basin. It's about 2,500 kilometers in diameter and as deep as 13 kilometers in places. But flooding has never filled it with smooth lava flows to make an obvious mare. The fourth stage, slow surface evolution, has been more limited on the moon than on Earth because the moon has cooled rapidly and also lacks water. Flooding on Earth includes water, but the moon has never had an atmosphere and thus has never had liquid surface water. With no air, no water, erosion is limited to the constant bombardment of micrometeorites and rare larger impacts. As the moon lost its internal heat, volcanism died down and the moon became geologically dead. Its crust never divided into moving plates, evident from the fact that there are no folded mountain ranges, and the moon is now a one-plate object frozen between stages 3 and 4. So in your own time, you can go through Practicing Science 16.2 and What Are We? And that brings us to the end of Earth and the Moon. And while we still have a bit of time left in this lecture, we can start with a new lecture. And in the new lecture, we're going to start now look at Mercury, Venus, and Mars, the other terrestrial worlds. So before we start, what can you guys tell me about these terrestrial worlds? Yes, Mars is red. Yes, so which planet is this? Yes, that is Mercury. And this planet? Yes, Venus. And then lastly, our beautiful Mars. So, who of you had ever had the opportunity to look at the planets through a telescope? So if you ever have the chance, please do. It is quite an eye-opener. So if it wasn't for COVID, we would have had an astronomy stargazing evening. But my three favorite planets to look at is Jupiter, Saturn, and Mars. It's really amazing, especially when you see Saturn's rings for the first time. So in a previous chapter, you compared a geological active planet, Earth, the larger of our terrestrial worlds, with the smallest, Earth's geological inactive moon. In this chapter, as you continue studying individual terrestrial planets, you can continue comparing the planets with each other, searching for similarities and contrasts. Like people, the terrestrial planets are more alike than they are different, but it is the differences that are most memorable. As you explore, you will be searching for answers to four important questions. Firstly, how is Mercury similar to and different from Earth's moon? Secondly, how does distance from the sun affect the planet and its atmosphere? Thirdly, how does size determine the geologic activity and evolution of the planet? And then lastly, what is the evidence that Venus and Mars were once more Earth-like and why they change? Mercury orbits so close to the Sun that it is difficult to observe from Earth, and little was known about it until 1974 when the Mariner 10 spacecraft first flew past Mercury and revealed a planet with a heavily cratered surface resembling a larger version of Earth's moon. Analysis of Mariner 10 showed that large areas have been flooded by lava and then cratered. Spectacular new images and data arrived from the Messenger spacecraft that flew by Mercury 3 times before finally setting orbit into around the planet in 2011, beginning a close-up investigation that lasted until it ran out of maneuvering fuel and crashed in 2015. Another thing, the Mariner spacecraft, Artemis Hook also did tracking and telemetry on these spacecraft. So in this figure, in figure A, we can see an enhanced color mosaic image of the Messenger spacecraft of the portion of the planet Mercury containing the colorless multi-ringed basin. The color enhancement emphasizes variations in composition among different parts of the surface. Then in image B, the origin of the spider formation photographed by the Messenger is still a puzzle. And in C, lobate scraps across craters, indicating that Mercury cooled and shrank, wrinkled its crust, and many of the craters had formed. The largest impact feature on Mercury is the Caloris Basin, a mountain-ringed basin that Messenger photos reveal as 1,515 kilometers in diameter, resembling the large ringed basin Mare Orientale on Earth's moon. The Caloris Basin on Mercury and Mare Orientale on the moon both include concentric rings of cliffs formed by a large impact. Though Mercury looks moon-like, it does have several features that Earth's moon lacks. Messenger photos revealed a spider of raised ridges appearing to extend from near a medium-sized crater. Geologists are not sure what processes could have caused the spider. Images from both Marinette 10 and Messenger reveal long curving ridges called lobate scraps up to 3 kilometers high and 500 kilometers long. The scraps even cut through craters, indicating that they formed after most of the heavy bombardment. The lobate scraps are the kind of faults that form by compression. This suggests that the entire crust of Mercury was compressed long ago. So when studying for your test, you can go through the exact comparison and profiles of the Moon and Mercury. Mercury is quite dense, and models indicate that it must have a large metallic core. In fact, the metallic core occupies about 75% of the radius of the planet. In a sense, Mercury is a metal planet with a thin rock mantle and crust. Spectroscopic observations indicate that Mercury has an extremely thin atmosphere that may be partly outgassed from the crust and partly captured from the solar wind. The accumulated facts about Mercury don't really help you to understand a planet until you have underlying hypotheses. Like a story, it must make sense and bring the known facts together in a logical argument that explain how Mercury got to be the way it is. Mercury is small, and that fact has determined much of its history. Like Earth's moon, Mercury has lost much of its internal heat, and this is no longer geologically active. In the first stage of its planetary history, Mercury differentiated from a metallic core and a rocky mantle. The presence of a magnetic field about 1% as strong as Earth's is further evidence of a metallic core. You learned in chapter 15 that a condensation sequence could explain a high abundance of metals in Mercury. But detailed calculations show that Mercury contains even more iron than a condensation sequence would predict. Drawing on the large impact hypothesis for the origin of Earth's moon, scientists proposed that Mercury suffered a major impact after differentiation that drove away much of the rocky mantle. However, data from Messenger include images of surface hollows in many locations, indicate that a substantial amount of volatiles were incorporated in the crust and subsequently vaporized. Abundant volatiles would not have survived a giant impact, so an impact may not after all be the explanation for the size of Mercury's metal core. Mercury is now a one planet, much like Earth's moon, and lacking a significant atmosphere to erode its surface, has changed little since the last lava hardened. In this image, we can see a mosaic of Messenger enhanced color images of a section of the floor and peak green mountains of Mercury's Radilati impact basin. The individual frames of the mosaic are about 20 kilometers wide. The rounded depression called hollows seen in many locations on Mercury may have been formed by sublimation of volatile components in the surface material. Now we're going to start looking at Venus. You might expect Venus to be much like Earth. Its diameter is 90% of Earth's. It has a similar average density and composition, and it is just 30% closer to the Sun. Unfortunately, the surface of Venus is perpetually hidden below thick clouds, and only in the past few decades have planetary scientists discovered that Venus is a deadly hot desert, world of volcanoes, lava flows, and impact craters lying within a deep atmosphere of hot gases. No spacesuit is tough enough to allow you to visit the surface of Venus. In composition, temperature, and density, the atmosphere of Venus is more Hades than heaven. The air is unbreathable, very hot, and almost 100 times denser than Earth's air. How do planetary scientists know this? Because US and Soviet space probes descended into the atmosphere and in a few cases landed and reported back from the surface. So if you Google it, you can actually see images of Venus surface. In composition, the atmosphere of Venus is roughly 96% carbon dioxide. The rest is mostly nitrogen with some argon, sulfur dioxide, and small amounts of sulfuric acid, hydrochloric acid, and hydrofluoric acid. There is only a tiny amount of water vapor. On the whole, the composition is deadly unpleasant and would certainly smell bad too. Spectra show that impenetrable clouds that hide the surface are made up of droplets of sulfuric acid and microscopic crystals of sulfur. So why the probes didn't last long on the surface of Venus is because of the high temperatures. Literally, it desoldered itself. The solder literally came off the PCBs and then everything failed. So here in this image, we can see the four main cloud layers in the atmosphere of Venus are more than 10 times higher above the surface than Earth clouds. They completely hide the surface. If you could insert thermometers into the atmosphere at different levels, you'll find the lower atmosphere is much hotter than that of Earth, as indicated by the red line in this graph. The strange atmosphere is 90 times denser than Earth's atmosphere. The air you breathe is 1,000 times less dense than water, but on Venus, the air is only 10 times less dense than water. If you could survive the unpleasant conditions, you could strap wings on your arms and fly in Venus' atmosphere. The surface temperature on Venus is hot enough to melt lead. And you can understand that because the thick atmosphere creates a severe greenhouse effect, sunlight filters down through the clouds and warms the surface. But heat cannot escape easily because the atmosphere is opaque to infrared radiation. Traces of sulfur dioxide and water vapor help trap the infrared, but it is the overwhelming abundance of carbon dioxide that makes the greenhouse effect on Venus much more severe than on Earth. Although the thick clouds of Venus are opaque to visible light, they are transparent to radio waves, so astronomers have been able to map Venus using radar. As early as 1965, Earth-based radio telescopes made low-resolution maps, but later both US and Soviet spacecraft orbited Venus and mapped its surface by radar. Maps made in the early 1990s by the Magellan spacecraft reveal objects as small as 100 meters in diameter. Radar maps of Venus are reproduced using arbitrary colors. In some maps, scientists have chosen to give Venus an overall orange glow because sunlight filtering down through the clouds bathes the landscape in a perpetual sunset glow. Other radar maps have been colored gray, the neutral gray of the rocks. In yet other maps, lowlands are colored blue, but there are no oceans on Venus. When you look carefully at colored radar maps of Venus, recall that its surface is a deadly dry desert. By international agreement, names on Venus are all female, with 3 exceptions: Maxwell, a high mountain, and Alpha Reggio and Beta Reggio, 2 high volcanic peaks, which were all named before the IAU naming convention for Venus was adopted. So the IAU stands for the International Astronomical Union. Radar maps show that Venus is similar to Earth in one way, but strangely different in other ways. Nearly 75% of Earth's surface is covered by low-lying basalt seafloors, and 85% of Venus' surface is covered by basalt lowlands. There is no liquid water on Venus, however, its lowlands are not really seafloors, and the remaining highlands are not like the well-defined continents you see on Earth. Whereas Earth is dominated by plate tectonics, something different is happening on Venus. The highland area Ishtar Terra, named for the Babylonian goddess of love, is about the size of Australia. At its eastern edge, the mountain called Maxwell Montes rises to an altitude of 12 kilometers, with the impact crater Cleopatra on its lower slopes. For comparison, Mount Everest, the tallest mountain on Earth, is 8.8 kilometers high. Bounded by mountain ranges in the north and west, the center of Ishtar Terra is occupied by Lakshmi Planum, a great plateau about 4 kilometers above the surrounding plains. The collapsed calderas Colette and Sakajiva suggest that Lakshmi Planum is a lava plain. The mountains bounding Ishtar Terra, including Maxwell, resemble faulted mountain ranges, which suggest that limited horizontal motion in the crust as well as volcanism may have helped form the highlands. So here is radar images of the surface of Venus. So here we can see Ishtar Terra, and if we zoom in, we can see the different Cleopatra ridges and Maxwell. As usual, you can learn more about other worlds by comparing them with each other and with Earth. Notice 3 important ideas plus 2 new terms. There are 2 main types of volcanoes found on Earth. Composite volcanoes are associated mostly with plate boundaries, and shield volcanoes are associated with hotspots that are related to plate boundaries. Volcanoes on Venus and Mars, unlike on Earth, has all the shape of shield volcanoes, the kind produced by hotspot volcanism rather than by plate tectonics. Some volcanoes on Venus and Mars are very large. They have grown to great sizes because of repeated eruptions at the same place in the crust. This is also evidence that neither Venus or Mars has been dominated by horizontal plate tectonics like Earth. Many features on Venus testify to its volcanic history. Radar maps reveal shield volcanoes and long lava channels. Other volcanic features include the corona circular bulges up to 2,600 kilometers in diameter, bordered by fractures, volcanoes, and lava flows. Corona appeared to be produced by rising convection currents of molten magma that push up under the crust. When the magma withdraws, the crust sinks back, but the circular fractures mark the edge of the corona. So here we can see lava flows to corona and these pancake domes from radar images of Venus. No astronaut has ever stood on Venus, but a few spacecraft has landed on the surface and survived the heat and pressure for a few hours. Some of those spacecraft analyzed nearby rocks and snapped a few photographs. The surface rocks on Venus are dark grey basalts, much like those on Earth's ocean floors. This is further evidence that volcanism is important on Venus. While you are thinking about volcanoes, you can correct a common misconception. The molten rock that emerges from volcanoes come from pockets of melted rock in the upper mantle and lower crust, and not from a planet's molten core. So here we can see images of the surface of Venus. So the Venera 13 lander touched down on Venus in 1982 and carried a camera that swiveled from side to side to photograph the surface. The orange glow is produced by the thick atmosphere. When that is corrected to produce the view as it would be under white light, you can see that the rocks are dark grey. Isotopic analysis suggests they are basalt. So here is how we see from the camera. And this is when we put a filter in place and see how it would be under normal light. Radar images show that Venus is also marked by numerous craters. The atmosphere protects the surface from stellar meteorites that would produce craters smaller than 3 kilometers in diameter. Larger meteorites penetrate the atmosphere and have formed about 10% as many craters on Venus as on the Maria of Earth's moon. The number of craters show that the crust is not as ancient as the lunar Maria, but also not as young as Earth's active surface. The average age of the surface of Venus is estimated from crater counts to be roughly 500 million years. Geologic processes are not renewing the surface of Venus as rapidly as Earth's surface, but no heavily cratered terrain or large impact basins remain on Venus from a heavy bombardment era. Here we can see impact crater Hell. In the foreground of the Malagen radar image is 37 kilometers diameter. Craters in the background are 47 kilometers and 63 kilometers in diameter. This radar map has been digitally modified to represent the view as from a spacecraft flying over the craters. So, ladies and gentlemen, I see our time is up, so we will continue our lectures next week. We are almost done with all our coursework. So have a great evening. Good luck with the rest of the week. And those that are writing the SIG test, I will see you tomorrow evening. Thanks everyone. I will remain active for another minute or two.